Hello my friends, in this session we will learn about the polysaccharides. Polysaccharides are complex sugars, they are called as glycans also, and these is a polymers of same or different type of monosaccharides, and formula as you know C6H2O, and this you can write here Y, and this can be your n number of molecules. These monosaccharides are connected by the glycosidic bonds, and typically normally this polysaccharides consist of 200 to 2500 monosaccharides, long chains, and these saccharides have linear or branched carbon chains. Okay, this much information is sufficient. Regarding classification, if you take the biological role, so on basis of this biologically we can divide in two parts. One is homopolysaccharides, other is heteropolysaccharides. So in homopolysaccharides, if you take storage and structure, in storage it is called as plants and animals. So in plants we have starch is the polysaccharides, while in animals we have glycogen, which is usually found in livers in maximum quantities and muscles. And if you take the structural type of homopolysaccharides, we have in plants we have cellulose, and in animals it is your chitin. Heteropolysaccharides are chondroitin, sulfates. This is one of the examples. So there are numerous examples in heteropolysaccharides also. So like we have heparin is there, agar is there. So we will see in another classification. So on the basis of number of type of monosaccharides, again if you take the monosaccharides, so we will have two types. One is homopolysaccharides, second is heteropolysaccharides, as like this one previous biological role. So in case of homopolysaccharides, it is again two types, pentosanes and hexosanes. So pentosanes two types, arabins, and next is a xylans, and in hexosane we have glucans, fructans, galactans, and your mannans. In glucans, if you see the examples is your starch, glycogen, dextrin, okay, dextrans, cellulose. So this dextrin is actually made from the sucrase enzyme, sucrose. So if you use sucrase enzyme in this will convert sucrose into dextrans. So dextrans is usually found in our teeth. Teeth you have a dental plaques are there. So dental plaques are due to the dextrans. So this is done by the enzyme sucrase. Fructan we have inulin, levin, galactans, and mannans. And in case of this one heteropolysaccharides, they are the complex polysaccharides. So they are heteropolysaccharides. So it is again different type of monosaccharides. Again we have examples: agar, gum, algin, and hemicellulose, and GAGS, glycoproteins, proteoglycans, mucopolysaccharides, which is amino sugars. So this mucopolysaccharides is our amino sugars. And the third type is your complex polysaccharides. So apart from homo, hetero, and this is joined by the non-carbohydrate molecule. So this is not that much important. So we will take only homopolysaccharides and heteropolysaccharides in our syllabus. So most common homopolysaccharides are starch, cellulose, and glycogen. What is starch? Starch they don't have any taste. Taste is not there, no smell is there, and number of molecules is 200 to almost thousands. It is a mixture of two different type of polysaccharides, that is amylose and amylopectin. The amylose is 20% and amylopectin is 80%. Of course, this is made up of, both are made up of glucose molecules. You can see this is starch, and if you give amylase in dilute acid solution, so undergo hydrolysis, this whole starch will convert to dextrin. So this is the N1 and this is N. So here almost N is more than that of N1. So this is broken down, and again in presence of dilute acid it will hydrolyze to give maltose, and maltose will finally convert to alpha D glucose. Or if you give diastase instead of amylase, if you give diastase on hydrolysis, it will convert into your this sucrose, and sucrose will give you on hydrolysis maltose. So then this is the cyclic chain is there. So starch solution, this starch solution, it will give blue color when you drop iodine solutions, and again if you heat it, this blue color will disappear on 75 to 80 degrees centigrade, and again if you cool it, and then you will get the appears again. So on heating it will disappear, and on cooling the color will reappear. What is amylose and amylopectin? So amylose is normally helicoidal in shapes, right? And it is your amylopectins. So if you take the percentage by, this is 20%, this is your 80%. Second thing, this is linear polymer, this is highly branched polymer, and in this case we have linkage alpha 1,4 glycosidic linkage. In this case here, glucose units are joined together by alpha 1,4- and alpha 1,6 glycosidic linkage, and number of molecule units is 60 to 300 units. In this case, so we have 300 to 600 units or more than that also. It is soluble in hot water. Amylose is soluble in hot water, while amylopectin is insoluble in water. So we will see some of the diagrams of this starch. So this is the diagram of amylose and amylopectin. So amylose, you can see there is a glucose alpha 1,4 glycosidic linkage there. This is 1,4 glycolic linkage. This is alpha, and this is your carbon is there, and 1,4 linkage is linear polymers. And in amylose, you can see this is your 1,6. So this is the alpha 1,6 glycosidic linkage, and this is alpha 1,4 in. So both the type of chain is there. This is branched one, this is linear. So this is together is your present in the starch. So this is our another diagrams of amylose, amylopectin. So in the form of your cyclic chain. So you can see this is chain is there, 1,4 1,4 linkage there for amylose, and for amylopectin you can see the chain. It is again it is continuing, and this linkage 1,6 linkage, 1,4 linkage. So both diagram, I hope you have understood amylose and amylopectin. So amylose is 20%. This is amylopectin is 80%. Here is a pictorial difference between amylose and amylopectin. This is a simple unbranched linear chain. This is branch chain, soluble, insoluble in water. Alpha 1,4 glycosidic linkage. Here alpha 1,4 1,5 glycosidic linkage. Blue color with dilute iodine solution. Here yellow or orange color with iodine solution. Molecular weight is 10,000 to 50,000. Here 50,000 to 1 million. This is the molecular weight is there. So unit wise different, and molecular weight is also different. Next, our homopolysaccharide is cellulose, and this is most abundant carbohydrate in nature. So if you take cotton, cotton is 90 to 95%, and in case of wood it is 50%, and the rest is in lignin. So this is, you can find cellulose used for making gun cotton, cellulose acetate, which is used for the artificial silk, that is called rayon. So these are the compound which we can make from the cellulose. It is insoluble in water, or you can say organic solvents, but it will decompose on heating but not melt. So cellulose cannot be melt on heating. It is dissolved in Schweitzer reagents, which is ammonical copper hydroxide solutions, copper sulfate plus ammonium hydroxide solutions. This is the complex. In this complex, it will be soluble. It does not reduce tolerance reagent and Fehling solutions, so it will not form ozone because of polysaccharides. It's not fermented by the yeast. It is dissolved in acidified zinc chloride solutions. When cellulose is treated with a concentrated sulfuric acid, so if you take the cold conditions, it will dissolve slowly, and when it is diluted with the waters, it will form a starch-like amyloid precipitate, which is called as parchment paper. When it is treated with it is boiling with the dilute sulfuric acid, it will form the D-glucose, and under the acidic hydrolysis, the cellulose will go beta D-glucose. It will form beta D-glucose. If you take concentrated sulfuric acid, concentrated sodium hydroxide, so the sucrose, the cellulose will convert into gelatinous semi-transparent mass. This will give you lustrous to cotton. So cotton becomes lustrous due to this one addition of concentrated sodium hydroxide. And this lustrous cotton is called as mercerized cotton. Means it will undergo mercerization. So it is called as mercerized cotton. Cellulose linear chain polysaccharides, it is of beta D-glucose, and it is joined by beta 1,4 glycosidic linkage. So the linkage is 1,4 glycosidic linkage, and the normal unit is 300 to 50,000 units are used. There is one more compound called chitin or chitin. This is chitin or chitin, you can say it is structurally similar to cellulose, and it differs as it has an N-acetyl amino groups instead of your hydroxyl groups. In place of OH groups, if you are using N-acetyl amino groups, then it becomes at carbon 2, so this becomes your chitin. So you can see this is your molecules of chitin, in which the second carbon is NHCOCH3, which is acetyl amino group is there. So you can see this linear chain with the help of glycosidic linkage there. So there are 3 subunits over here. And in case of cellulose, you can see the hydrogen bonding. So it is very strong molecules which have hydrogen bonding between the 2-3 subunit of in cellulose molecules. And you can mark here this CH2 is this side, but this is the flipping of this compound. So both the hydrogen bonding take place. So this intermolecular hydrogen bonding. And if you take second structure of cellulose, so this is your beta 1,4 glycosidic linkage. So this CH2 all OH6 carbon is in the same side, but in this 6 carbon is opposite side. So here alpha 1,4 glycosidic linkages are easier in this case to hydrolyze than the beta 1,4 glycosidic linkage. This means the starch is very easy to hydrolyze, but cellulose not easy to hydrolyze because of anomalic effect. So due to this anomalic effect, it makes the it weakens the bonds to the anomalic carbon. That's why starch is more easily soluble, while cellulose is not easily soluble. Next is our glycogen, which is multi-branched polysaccharides. So this is also animal storage food. And the structure is again similar to amylopectin. If you remember, amylopectin is branched, but this glycogen more branched than amylopectin. So we can say with one branch again 8 to 12 glucose units is present. So mainly it is stored in livers and muscles. So this is a diagram of amylopectin. You can see it has some 10 residues. Means you can count it 1, 2, 3, 4, 5. Like this there are 10. So just remain you can imagine. So the other units are there. Okay, but here again in further unit it is further divided. So it is more branched in the one. So if you keep branching from here also, it becomes your glycogen. So glycogen is more branched. Amylopectin you can see there. So per branch is 10, here per branch is 24 subunits are there. Only this is the difference. It is again made up of cellulose, glucose. Glycogen is the high degree of branching. It has some physiological effects, means physiological importance. Why? When body needs energies, then this individual that is branch units, it will simultaneously remove from the ends of many branches. So this is the advantage of the branch units. You will get the more energies. And the last we will see the heteropolysaccharides. So they are the certain two or more different kind of monosaccharides or their derivatives. These heteropolysaccharides. This will provide the extracellular support for the organism of all kingdoms. So it can be also branched and unbranched. So this we have not studied too much in details. Now we will see some pictures of all these starch, cellulose and glycogen. So this is the picture of glycogen. Glycogen more branched. You can see the in terms of branch, this is the 20 to 50 nanometer size. So this is the branch molecule of glycogen. So alpha 1,4,1,6 linkage is there. So and if you see the glycogen structure, so this is the glycogen structures. Here we have again alpha 1,6 linkage there, alpha 1,4 glycoside linkage there. So I hope you have understood the glycogen structures. In this diagram, you can see the size of the cellulose microfibrils. This is the cell walls, and cellulose is present in the plant cell wall. This is the microfibril, and in this, if you take out one microfibril, there are so many microfibrils are there. So out of this microfibril, if you take one, so this is the structure of glucose molecule. You can see one is going this one is going this one. So these are the cellulose molecules which have beta glucose there as a monomers. This is the one type of diagram. Again, if you take some other diagrams like this is there, so both are almost same. So this is present in the, you can see this is the plant cell wise there from the leaf. Again, on enlarging this whole structure, you will get these structures. This is the cellulose fibril, and from this again you can see the microfibrils are there. So this is the diagram of microfibril. So you can understand this is the hydrogen bond is there. So the cellulose are bonded by the hydrogen bonds like this. And these are the glucose monomers. So this is diagram of cellulose. You can see this diagram is, so beta 1,4 link is there, and this is the how it is making a linear chains. And this is the diagram of cellulose 1,4 linkage of beta glucose molecules. It is very carefully, just pause the video and you can see the structures and note down. So this is the structure of the amylose in the helicoid structures. You can see, and amylopectin is, you can see branch structures. This is the glycogen structures there, and this is the structure. You can see clearly, once is glycosidic bonds, branch chain, and again is the how it is connected. You can see these structures. So I hope you understood amylose, amylopectin, and glycogen. So let us see the difference between all these compounds. So this is the more clear pictures. So amylose, you can see linear, amylopectin is like this one, and glycogen this one, and cellulose is just cross-linked. And if you see the difference, cellulose, plant is animal food. This is the beta glucose, alpha and alpha. So only this is beta glucose, remaining alpha. Bond wise 1,4,1,4. So you can remember 1,4,1,4. This is 1,4,1,6, 1,4,1,6. So this is only exception, remaining is same. Here branches no, here branches no. Amylose, here 20 subunits, here 10. And diagram wise you can see clearly, this is a linear, this is branched, and shape wise already we have seen it. So this is for amylose, amylopectin, and this is glycogen, and this is for cellulose. So we'll see more difference. So here is the combined difference of all the compounds: amylose, amylopectin, cellulose, and glycogen. So if source wise, this is a cytoplasm. This is a matrix and cell wall. This is liver or muscle cells. Formula wise almost same. Structure we have discussed. This is structure of amylose, amylopectin branched. This is again linear. Again this is glycogen, more branched. Diagram of also we have seen it. Amylose, amylopectin. This is your glycogen. This is starch. And composition. If you see the composition, so we have seen the composition. So 60 to 300 alpha glucose, 2000 to 6000, 3000 beta. So these numbers are maybe variable. Alpha 1,4 linkage, alpha 1,4,1,6, alpha beta 1,4. This is only beta. This alpha 1,4 or 1,6 linkage. So in these two cases, amylopectin, glycogen, both are more same. So linkage also same, but these two are opposite to each other. Helical, curved, linear, curled up, globular. It is unbranched, highly unbranched. This is more highly branched than your amylopectin. This is unbranched. Tightly packed hydrogen bond, loosely packed, tightly packed hydrogen bond, loosely packed. This means amylose and cellulose are your tightly packed with hydrogen bonds. Soluble, insoluble, insoluble, and soluble. Slowly hydrolyzed, rapidly hydrolyzed means this is amylose and glycogen will be slowly hydrolyzed. These two will be rapidly hydrolyzed. Long-term energy storage. This is your starch. Glycogen is again short range. Structure wise, this is structure rigid, chemical also resistant, insoluble. This short-term energy storage. Now importance means they have many type of polysaccharides used for important for digestions. Crabs in foods are broken down by specific enzymes in crabs. So examples they have animals have amylase to break down alpha 1,4 and alpha 1,4 glycoside linkage in starch, but it will lacking cellulose enzyme to break the cellulose. So different carbs for the different organism according to the enzymes present. So this is the crabs. So in different crabs there are different type of enzymes. If they have cellulose enzymes, they will break the cellulose. If they have a starch enzyme, so they will break the starch. So here you can compare the diagram for polysaccharides. So this is the inulin homopolysaccharide. This is the hyaluronine. This compound is there. So something typical name is there. This is starch. Chitin is there. This is cellulose, heparin. This is your dextrin, chondroitin sulfate. So this part is your homopolysaccharide, and this part is your heteropolysaccharides. So again you can see the structure of this glycosaminoglycans, which is called as GAG. So this is the GAG is there, glycosaminoglycans. So this is the hyaluronic acid. So hyaluronic acid is there, and this is the chondroitin 6-sulfate heparin, and this is derman sulfate is there. So this is a structure. So you have to see the structures. Learning is not that much important. So this is a difference by this NHCO CH3 group is there. For GAG or for you can see the chitin also there. So this is our final diagram. You can compare structural polysaccharides and nutrient polysaccharides. So inulin, para-amylin, glycogen, starch, amylopectin, amylose. Here is cellulose, mannan, chitin, hyaluronic acid, peptido, glycans. This is a source. You can just pause this video and just see this one, and you can see the composition also. And here is a different type of linkage. So just pause it, wait for some time, just watch it and understand. And I hope you have enough information for this polysaccharides in this video lectures. So thank you very much.